Okay, for those of you who don't know me, my name is Justin Monroe. I'm with the ARM Data Quality Office, and so I'm going to try to run a basic tutorial here, tell you a little bit about ARM's NetCDF files and just the basics, and then how to open a file in Python, interact with the data a little bit, and make a couple of simple plots. And so hopefully you'll get something good out of this. I unfortunately won't be able to go through all the basics of Python. We're just going to have to jump into some things, but hopefully it won't be too complicated. I also, in the way I've done this, I've created this notebook. So this is an IPython notebook. It actually allows you to mix text and code in a web browser. And for those of you who are familiar with other languages where you can load up kind of a IDL or MATLAB, load up an interactive shell where you can sit there and type commands and make a plot, things like that. Python has something similar. You can run interactive shell in Python, and this actually allows you to do that on the web browser. So we're going to do that later. We're going to actually be able to run code from the browser and see what the output looks like in the actual browser window. So this actually is a really nice mechanism for describing all this. So first I'm going to start with the ARM NetCDF files. Hope everyone here has probably at least heard of NetCDF, but maybe just isn't familiar with how to read it. So I've got some information here. I won't go through all the details, but this is the file format ARM uses for the data. And it's created by Unidata. It's kind of a compact. It's a binary file format, but it's really nice because you don't have to worry about, if anyone's worked with say Fortran, like Big Indian and Little Indian, and different compatibility between machines and all that, takes care of all that for you. And it's really nice too because it's self-describing. It contains all the metadata as well as the data. So if you want to know the variable name, like the long name, the units, all those things, that can all be added to the file. So I'm sure some of you may have even used Fortran or C or something else to access these files before, but as I described here, a lot of people in ARM are starting to use Python, and I think it's actually a lot easier in some respects. I mean, depending on how much background you have in another language, you may not agree, but so I'll go down here and we'll start with just the general file format for ARM. So there's a lot of information here, but every ARM file name should be constructed this way. So we have different components of the file name. We have a site, which is a 3-letter ARM site identifier. So say SGP for Southern Great Plains. We have an instrument code, which could be something like MET for our surface MET observations, or MWR for our microwave radiometer. Or it could be a VAP, evaluated product, so maybe it has a specific name for that product. We may have other qualifiers after that if you want to describe it further. Then we may have temporal designations describing the sampling resolution if it was average at 30 minutes or something like that. And then after that, there will always be a facility ID. And so at our Southern Great Plains site, we have several extended facilities, so this is telling you which one the data refers to, where it was collected. And then lastly, there is a data level before you get to the time or date and time. So it's always going to be, the standard 8-digit date, and then a 6-digit time in hours, minutes, and seconds. And that actually refers to the start of the file. So your first data point in the file. And so the file we're going to start with in the tutorial is just a simple MET data set, or standard MET observations. And so that's the file I provided in the email as SGP MET E13.v1. So this is from the E13 extended facility, which is actually at the central facility in Lamont, Oklahoma. And we're doing February 18th, 2014. So you can see I've broken out the various components as it relates to the text above this file. So our typical file contents, as I mentioned before, the NetCDF files contain a lot of basic metadata describing the actual data. All ARM files will have one or more dimensions. So you can imagine you have to have a time dimension if you're measuring things over time. So that will always be an ARM file for the most part. I don't know if we even have any that don't have time. But you may have things that are measured in 2 dimensions, like time and height. So maybe a classless cylinder, backscatter profile, something like that. And you may even have 3 dimensions depending on what you're looking at, like a scanning radar or something. So that's one thing you'll find in the NetCDF file is the dimension. If we do have variables that are dimensioned by or that have multiple dimensions, time will always be the first dimension. So that should always be the case. The files also contain all the variable names and data types for the variables. Then I'll have all the attributes, so maybe we have a valid min or a valid max for the data. We say, oh, we don't want the temperature above 50, so that is described in the valid max in the attributes. And then lastly, we'll have global attributes, which these apply to the file as a whole, not a specific variable. So these are just general information such as maybe the software version, the history, when it was processed, instrument serial numbers may be in there, a whole number of things. There could be technical report references, or if it's a BAP, may reference a peer-reviewed journal article, things like that. So I'm just going to show an example of the header for the file that we'll be using first in the tutorial. So if you go to Unidata and you download NetCDF and you install it, it will come with a suite of system utilities. One of them is NCDump, and so I'm just showing the output from NCDump. I have a link here if you want more information about that. And so this is actually the file header for the SUQNet file. So you can see the first thing listed is the dimension. So it's time, and that's the only dimension in this file, because these are just simple met observations. And we have 1,440 time samples in this particular file. And time is always what they call the unlimited dimension. So if you're combining files together, you always want to combine along that dimension, for obvious reasons. So then we have various variables in the file. We have a base time and a time offset, which I won't go into the details of those right now. It's basically the base time is the start of the file, and then offset is an offset from that. And then we have a time variable, which is basically just a delta from the start. It's basically just 0, 5, 10. You can have a delta from the start of the file. It has actually no relation to the actual time and the values themselves. We can have QC variables for each variable. So if you have a QC variable, it's a quality control. It will be QC underscore and then the variable name. But you can see we have various variables in the file: atmospheric pressure and so on, mean temperature, and we have various attributes listed for each one. So the long name, the units, valid min, valid max, and so on. So we can scroll through all these variables, and you can see there are quite a few in the file. If you want to know what's in a file, this is the way to do it. Look at the file header, either through NCDump, or I'll show you a way to look at it in Python in a second. There are actually a lot of utilities out there for doing this. And of course, you got your latitude, longitude, altitude. And then here are your global attributes for this particular file. So some of the things I mentioned, like the software version, get an averaging interval. So lots of useful information that you may be interested in. If you ever wonder if you're using the same version of a data set that you got earlier, is the place to check. Look in the global attributes. The version number should change. So now I'm going to get into the part with actual code. So hopefully everybody has this working. If you don't, I sent out an email about an hour ago, I think, that has a link to the notebook where you can at least view it. You just won't be able to interact. You won't be able to run the code, but you can at least follow along. So what we have here now is a cell. This is actual code. So you can actually click in here and make changes to it. So I sent out an email before when I asked everyone to download the NetCDF files. This is the first place where you would actually change the path to wherever you downloaded those files. So I hope everybody's done that. Does anyone need some time to go through this? Everyone think they have it working? Okay. So first thing we're going to do here, I actually gave you guys the notebook with all the output already there, but that's no fun. So go to the top menu where it says Cell, and go to the All Output menu here, and just go ahead and clear it. So that should clear all the output in your notebook. So now we're actually going to run this and see what happens. Hopefully you guys will get something, the same thing that I'm getting. So, all right, the way Python works, you load it up. If you're in the interactive shell or if you're writing a script, it's going to have a standard set of functions and libraries that are like kind of loaded in the namespace by default, but some of them won't be. So NetCDF files, it's not a standard part of Python. It's a third-party library that we had to install separately. So you're actually going to have to import that manually. So this is just an import statement. So this is the thing I asked the Windows users to install separately because it wasn't included. So it's really easy. You just say from netcdf4 import dataset. So that's the first line. We're importing this dataset function, and that's the actual function we're going to use to open the file. So once that's imported, well, actually after you set your path to your file name, we're storing it in a variable called file name. Then you can just call this dataset function on your file name. So what we're doing is I'm calling this file obj for a file object. It's essentially storing everything that was in that file into this file object variable. And that's another thing in Python that is really nice. Everything in Python is actually an object. So once you start really learning it, there are actually various functions, or you can call them methods, that are attached to the objects by default. So you can basically run these as a dot notation right off that object reference. And so I'll show that here in a minute. So we've got this file object loaded into memory. This actually contains everything that's in the NetCDF file now in memory. So we just want to print it and see what we get here. See what's in that file object. So if we go up here and you hit this run cell button, the play button, while you're highlighting this cell, and your cursor can be anywhere in there. You run play, so you get output now. So I'll scroll back up, because it pushed me down a little bit. So this is going to give you the type. So this is the Python type. So it's a NetCDF4 .dataset, which makes sense because we imported dataset from NetCDF4. So that's the type of object we have. So it's also telling you what kind of NetCDF file it is. All ARM files are actually NetCDF version 3. We haven't moved to NetCDF4, so it's telling you it's NetCDF classic file format, version 3. Then what this is giving you is all the global attributes that were in the file header that I showed you above from the ncdump command. So you can scroll through that and see all those. And then as you scroll down, there's a little dimensions key here. It says time, so that's the dimension in the file. Then you have a whole list of variables. So these are all the variables that are in the file. So just hitting a print on the object is giving you quite a bit of information about what's in the file right there, without doing anything else. Is everyone able to do that, or no? Okay.
So the blue box is, we click in that, everything in that box gets executed?
Yes.
Okay.
Yeah, everything in the cell gets executed at once, unless I split it up into separate little commands. But yeah, so everything in the gray box or blue box, however it looks on your screen, gets executed once. So in this case, I have one command on the next line, and this is just this one command to get executed. So let's say you only want to see the global attributes. So as I mentioned a minute ago, we now have this file object, file obj, stored in memory. Well, there's a nice function that's built into the NetCDF4 module that we imported earlier called NCATTRS, which is basically NetCDF attributes. It's kind of short for that. And so if you're referencing that off the file object, that's the file as a whole. It's going to give you the global attributes. It's going to give you a list of them. So if we run the cell again, now you can see these are all the global attribute names. So you can think of this as kind of keys and values. So here you have all the names of the attributes. You have one called command line, process version, and so on. If I scroll back up here, you can see the command line actually has a value after it that ingests all this other information. And the process version has a version. So what we just did here is just print the attribute names, not actually what's stored in them. But just using this function, that'll give you a list of names. And then after that, you can see what you have, and you can access them directly. So now you can say file object.history if you want to actually see what's in the history attribute. So we'll run that. So there's actually the text of that attribute that was stored with that key. So what's contained in the history attribute. And there are actually a couple of ways to do this. So you can imagine if you're running a lot of code or writing up a script, you actually have to hard code this in there. You can say .history or .process version or whatever attribute you wanted. If you were writing a script and you didn't know what the attributes were called before that, there'd be no way to access them. So there's actually another function you can use called get NCATTR or get NC attribute, and then you can put a string in there called history. And you'll see that actually gives you the exact same answer or value. So if you're writing code where you need to loop over a bunch of unknown attribute names or something, this is probably the way to go. If you just know what you want, you can just do the .history the way I did in the first example. So as I mentioned, in addition to the global attributes, you've got your dimensions. So this is actually really nice because you've got this file object which has everything in the file. If you want to know what the dimensions are, well, you say .dimensions, and we just want to know what the actual keys, as I mentioned earlier. So you just say .keys in this case. So I'm sorry, I did the wrong one. That was the variables. Okay, so there, you have a list with all your dimensions. So it's just time. There's only one in this file. The U just means it's a Unicode string stored in there, so you can pretty much ignore that. But that'll show up next to all the strings here. So in the next example, which I already did, we want to know what the variable names are. So you can do file object.variables.keys. There's a whole list of variable names.
Sorry, question. What does keys refer to again? Sorry.
So this is something I didn't get into. There are different data types in Python.
Okay.
So you could have like a scalar or an array, or you could call it a list that stores multiple values. There's also something called a dictionary.
Right.
And if anyone's familiar with Perl or other languages, it's like a hash. So it's basically saying you have a key that can point to anything else. It can point to a scalar, it can point to an array, it can point to a string. So that's just the way this is stored in here. The variables are actually stored kind of as a dictionary. So you just want the keys to the dictionary. So you're saying, I want to actually see which keys are here, which variable names. And then I can go access them later when I actually know what the names are. So if you see in the next example, I'm actually calling that specific key. So I want to know what is actually stored in the temp mean variable. So before we created a file object which referenced the entire file, and all of these methods that I call NC attribute refer to the file object as a whole. So because we were referencing the entire file. So let's say you want to know what's just in that variable. We can create an object that just references that variable. And so now I'm saying file object dot variables temp mean in brackets here. And so it's just one of the variable names that you saw on this list. So we're just going to go with temperature. So now you can actually print that reference to the temperature object. So now you just get information about that specific variable. So the data type, it's a float, the long name units, and so on. You get all the values. The current shape of the array, it's 1440 values. It gives you the unlimited dimension and so on. So it's pretty nice because a lot of it is very similar to what we just did before. So now, if you want to see the variable attributes, it's the exact same function name. It's just referencing the variable object instead of the file object. So this NCATTRS, exact same name, but it's off temp object instead of file object. And that will give you all the attribute names in a list. It's the same thing we just saw up here. And then, like I mentioned before, with the global attributes, if you know the name, you can reference the variable attribute directly. You can just say, I want long name. And so we have this temp object. There you go, temperature mean. That's the long name. Or you can use this function with a key name. It's the exact same function we used before, just referencing the variable. So here's where one difference comes in between the global names, or the file object and the variable object, is we might want to actually access data. So in order to do that, you put this bracket with a colon in it, which is basically say, take the entire array, just pull it into a variable. In this case, I'm just printing it. I'm not actually storing it in a variable. And so those are some of the values. You can see the dot, dot, dot. It's not going to show everything on the screen, but those are the temperature values in the array from the temperature object. So now, I'm going to work on the next section here, which is going to get a little bit into working with the data. So everything that is loaded into memory in Python from the NetCDF4 module is loaded into what they call a numpy array. So this is actually a third-party scientific module, which is much faster than the basic Python list. It's all coded in C in the background. It's made for scientific computing. And I put a link here to a tutorial that talks a little bit more about it. There's a lot of documentation out there. So as I showed just above, I was just printing the temperature object. Here we're actually going to store it in a variable called temp. So I'm saying put all that data in the temp variable here. So then, if you're familiar with other languages, you can do various indexing, slicing on the arrays, and so on. Here I'm just saying I'll print the first 8 values. I'm doing colon 8. And there's your first 8 temperature values that were in that array. And so this is out of your NetCDF file. And if you want to start from the end of the array, you can put a minus first, and it'll actually go backwards. And so we want to print the last 8 values. I'm saying -8, colon, just go to the back to the front of the array. I'm sorry, that's wrong. Go to the end of the array. Now here I'm going to store a new array with the first 3 values. So just new temp equals temp 3. Really basic stuff here, but you can print new temp. So there's your new array. It only has those 3 values. So you just assign it to those first 3 in the temperature variable. So one nice thing is, and this isn't unique to Python, but once it's in this array format, mathematical operations like multiplication, addition, and so on apply to every value in the array. You don't have to do a loop. So this is actually where you get some of your performance gains by cutting out those loops. So here we want to convert all the temperature values to Fahrenheit. So I'm just saying F temp for Fahrenheit temp. And this is actually, I'm just using these 3 values we did here in the new temp. So I'm saying times 1.8 plus 32. So it'll actually do that to all 3 values at once. And so you can see we've got 3 new values converted to Fahrenheit. So it's pretty simple. Let's say you want all the temperature values. So we're going back to our original temperature array that had everything in it. But we only want the ones where the temperature is less than 2 Celsius. So you can actually put in your index temp of temp less than 2. So if we run that now, there are all your values that were less than 2 in the array. So you can actually put greater than 5. You can put whatever you want in there, any kind of a check. So that's really handy. As I mentioned before, everything in Python is technically an object. So there are all these different functions and things that are built in. If you want to see everything that's attached to an object, you can run this dir function on it. This is actually built into Python. You don't have to import it or anything. So we'll just run it on the temp variable. So you can see a lot of stuff pops up here. Some of this you probably want to look up if you're interested in it. But you can see there are various attributes and functions. There's a max and a mean and a min. I'll show those later. So if you want to just calculate the max of the array, it's very simple. It's .max. There's also a way to get more detailed help information from this shell. You can run this help command. I commented it out because it's really long, but I'll go ahead and run it here. So this actually gives you more information about the variable, and you could go through this and read about it. So I'll just scroll down past that. Yeah, it's really long. Wow. Okay. Maybe I should close it. There we go. Okay. So maybe you want to know the length of the array. You can run, there's a built-in len function for length. So we can run that on the temp. And so you see we get back 1440. Now that'll only give you the length along the first dimension. If it's a 2-dimensional array, you won't see that. So there's actually a command built into NumPy, which, as I mentioned before, the data type. This is the scientific array library. You can do .shape, and that'll actually give you the shape of the array, like both dimensions. And so in this example, I'm first printing the shape of the temperature array originally, and then I'm showing how you could actually reshape the array. There's actually a function built in called reshape. And so we know we have 1440 values. Let's say for whatever reason you want it to be 720 and 2. You can do .reshape, 720 and 2. So I'll print both of those. So there's your shapes. You've got 1440 on the temperature, which is what we had originally, 720 and 2 now on your new temperature that you reshaped. And these are some of the basic functions. When I was doing that directory function earlier that showed all this stuff that you might want to look into. Some of those were min, max, mean, standard deviation, sum, and so on. So I'm just showing how easy that is. Temp.min, temp.max, .mean. So if we run those, there's all your values, your sum, and so on. So there are a lot of different basic statistical functions and things that are built in to the array library. So I'm going to move on here. So first, now I'm going to get to creating a basic line plot. So just your bare bones, just line plot. Nothing fancy. So at the start of this, I had to add this command called matplotlib inline because we're actually using a library called matplotlib. So anyone who's familiar with MATLAB, that's where this gets its name. So the guy who created it was a MATLAB user, got tired of paying for MATLAB, and just wrote this thing in Python. And so a lot of the functions are actually the same name. If you're familiar with like P-color and P-color mesh and those things in MATLAB, they have the exact same things in this. So in order to render this in the notebook, you have to add this command, this %matplotlib inline. That's all that's for, is to render your plot in the browser. You would never use that if you were just coding something in a script. You would save it to an image or something like that. So just explaining that here. I have a comment there. So again, this is a third-party library, and we have to import it. It's not going to be loaded by default. So there's a nice function in matplotlib called subplots. And you don't necessarily need it to make a single plot, but you can. And if you're going to make any multi-panel plots, this is probably what you want to use. And so I think it's just easier to use this all the time. So that's why I'm starting with the subplots command. So the nice thing is, once you import the subplots, you have almost everything you need to do whatever you need to do. So in order to use this command to create a single plot with no other panels, just a single figure or axis, you can just call your figure and your axis equal to the subplots function. So what that's doing is creating a reference to the entire figure called fig, and then a reference to that specific axis where the data are going to be plotted called ax. If you had multiple plots, you would have multiple axes, but this is just a single plot, so we don't have all that right now. And if you had multiple plots, you'd have to set your number of columns and rows. That would all be a part of the subplots function. Right now we have an empty parentheses for a single plot. So that's how we're actually creating the initial reference to your figure and your axes. So then now you have your axis, and you just want to make a plot of temperature. So there's a plot function. You just call ax.plot. And you've got your temperature already stored in that array. You plot the temperature. So that's actually literally all you need to make the plot. I mean, that's just very simple as it gets, just a line plot. So I've actually added a few optional commands here just to show some other things you could do. So then you want grid lines on your plot. So there's actually something called grid. So ax.grid. If you want to set your x limits. So we have 1440 values. Python uses zero-based indexing, so I have 0 to 1439. You want to set a title on your plot. I've just added that, x.set title mean temperature. If we run that, let's see here. Oh, maybe I wasn't highlighting it. There we go. Okay. So there's your plot. Pretty basic, just regular numbers on the axes, not formatting time or anything. And you can see if I go back up here and comment this code out, if I say I don't want the grid anymore, comment it out, run it again. There's no grid lines. The reason I set the X limit, you'll see by default, okay, I've actually made this go to the end of the data, but if you didn't do that, it's going to actually add some white space by default at the end of the plot. So you can play around with this. There are actually all kinds of functions in the documentation. And I've actually added later on, after the tutorial, I don't know if we'll get to any of it now, which we actually might have time to get to some of it. I added some more advanced examples that get into a little more detail about formatting times and things like that on the plot. So does this make sense to everybody? Okay, creating a simple plot, loading the subplots function from your matplotlib library, creating a reference to your figure and axis. Nobody wants to speak up. Okay. Okay.
What's the variable fig for? Define it, but you can use it.
Okay, you have to define that when you create it. Now, there actually are various things you could do with that. Like if you wanted to save this as an image, there's actually a function called savefig. So you do fig.savefig and then the name of your file, like PNG or whatever.png. I didn't get into those details here, but there are various things you can do that manipulate the plot as a whole from the figure variable. And the reason you want that is if you're doing a multi-panel plot with like 6 plots on it, maybe you want to do something that references the entire figure, not an individual axis. So I may actually have to, yep. I did not put my new path here. I sent this out to you guys, so let me scroll up here real quick. Just copy this. See, I'm the only one, not the only one who wasn't prepared. So this was actually the last example I had in the basic part. Looks like we've gone a little faster than I expected here. Okay. So in this example, I actually started over and gave you like all the code as a whole as you would need it if you wanted to make this two-dimensional plot. So you remember earlier in the notebook we imported this data set function already. I just went ahead and did it again, and I went ahead and loaded the file here. And this is actually the other, the second file you were supposed to download. This is for the biosolicylometer. So it's going to create a 2D plot of the backscatter in the biosolicylometer file. If you wanted to see all the information in the file, you could do the same thing I did above with the MET file, as far as accessing the attributes, variable names, and so on. But I'm not going to do that here. So here, I'm importing the same subplots function, and then I'm also importing a color bar function to make a color bar for the two-dimensional plot. And I'm also importing from this numpy library a log function that basically take the log of the backscatter before we plot it. So, the same thing we did before. We have a file name pointing to the path where we have the file downloaded, and we're creating a new reference to that file. I'm calling it file object 2 here, just so it doesn't clash with the other one. And so then we want a variable called backscatter, or I've called it backscatter here. And you can see I'm doing multiple things at once here. So I'm actually taking that file object reference to the variable backscatter, pulling in all the data, and taking the log of it in one command. So you can actually do that if you want to, or you can take several steps, whatever your preference is. So the new array that I'm going to get here is going to be all that backscatter data after the log has been taken of every value stored in that variable. So since we're making a single plot, it's the exact same thing as before with the line plot. We're saying figure axis equals subplots. So here I'm just showing the shape of the array because there's something you actually have to do before you plot a two-dimensional variable in Python. If you want the time, at least with ARM data, if you want the time to be on the x-axis, you have to take the transpose of the array, or it will plot time on the y-axis. So that's just something you have to figure out when you're doing this, but I'm just showing you here. And there's actually a transpose function that's built into the array library, so it's real simple. You say backscatter.transpose. So we're going to store that into the backscatter array. So before we said ax.plot and we made a line plot. Well, that's the command for a line plot. One we want to use for this two-dimensional plot is called p-color mesh. It's like a pseudo-color mesh, basically. And it's the exact same thing as before, but we're just saying ax.p-color mesh backscatter. So we've got our 2D field in there.
Why didn't you have to do the transpose for the temperature plot?
Because it's a one-dimensional variable. For whatever reason, the way it handles a two-dimensional variable, it has something like time and height or time and range. It gets jumbled up, I guess, going between reading from the file and doing this plotting command. I guess it just has to be the other way. That's the only way I can answer it.
Okay. I guess I don't understand why it's going to try to put time as a y on the y-axis here, but it didn't for the...
Yeah, I guess it's just the way this function was implemented, the way it reads in the data.
It's similar to MATLAB. In MATLAB, the matrix is ij. It's based on
Right.
image processing, so the indexing starts at a different
Okay,
location.
yeah.
It's the same deal with IDL too. Yeah. Okay.
Right. So it's just something you need to know. If you want to plot time on the x-axis, just take the transpose. So in this case, I'm actually referencing this plot with a variable I'm just calling p-plot. And the reason I'm doing that is because I want to make a color bar later. So I can then use this color bar function that we imported above and then put the reference to the pseudo-color mesh plot here, the p-plot. So that's saying make a color bar based on that plot we just created. Before, when I did the ax.plot, I didn't make a reference to it because I didn't need to do anything else with it. So in this case, I did. That's the only difference, really. So as before, I have, the ax.grid, the set xlim, set ylim is another one. You want to set the y limit. Then I'm setting a title. So this is pretty basic. So if you run it, it might take it a second, but you should eventually get a two-dimensional plot. And so there you go. There's a little backscatter profile from the oscillometer. with a color bar. Nothing fancy. We haven't labeled the time or anything else like that. If you didn't set the X limit and the Y limit, the default plot is going to include white space in both directions, I think. So you can see that here. I rerun it after commenting that out. So that's why I did that. But you guys can play around with this, do whatever you want. I mean, you can run, if you want to set the title to be something else, or you can actually do a lot of things. You can set X labels and Y labels. So I'll just go ahead and go down. We've still got 20 minutes. I'll go into the next section if everybody's okay.
Are you going to talk about how to add actual time on the X-axis?
Yeah, so that's actually something I put in this more advanced topics section.
Okay.
I didn't know if we'd even get to it. So it looks like we have time, so I'll go ahead and go down here. So this is just showing how to combine strings in Python. So there's a function called .join, which is built into Python. And you want to use this because if you can use a simple plus operator, but if you're doing loops, it makes multiple copies of things that you'll run out of memory. You'll take a big performance hit. So you want to use this .join function. Just get in the habit of using it if you're combining strings in Python. So it's really simple. It's just, and this is built in. You don't have to import it or anything. So in this example, I'm just saying .join combined. And so if we run that, you now have those combined. And so the way this works, you have two parentheses, .join, that's your delimiter. So if there's nothing in there, it's just going to combine them as if there was, just using plus symbol. The next example, though, I have a comma and a space, .join 1, 2, 3. There you go, 1, 2, 3. So you got a new string. You can also put things in there like new line characters. So in this case, you got first line and second line. So I'm just showing you can do a lot of things with this .join function. And the reason I show this here too is I use it later in some other examples. So hopefully that wasn't too difficult. I really wasn't that advanced. So here's where I show getting the time to the right format to plot. So there's actually a really nice function built into the NetCDF4 library, and it's called num_to_date. And all it needs is the time delta from the start of the file. It doesn't even need to be referenced to an epoch 1970. It's just a delta from the start of the file. And it just needs the units, and they have to be, I think, UD units compliant, which most ARM NetCDF files are, almost all of them. So in this case, we're going to reference that first file object we opened above with the metadata when we made the temperature plot. And so I'm actually pulling up the time variable now. So I'm doing .variables time. And that's our time object. So next I want to get the units. So I'm going to use that function I referenced above. I said I want the units. And I'm going to store this in the time units variable. Then I want the actual data values. So it's the same as before with the array slicing. So then you just call this num_to_date function on your time values and put your units in there. And it does the conversion for you. So what this does is it converts it into the native date time format in Python, which can be used in the plotting libraries.
In doing this, you're redefining what times is, because you have...
Right, I am redefining it,
yes,
in this case. Because I did store times as just the deltas, now I'm saying change it to this date time format. So you pass it to this function, which is built into the NetCDF4 library, you just import it and run it. There we go. So now you have this array of actual time values, and you can see it actually has the dates and times in it. So if you would have just printed the times before, which I'll just do that. I'll print times before we do the conversion. And rerun this. Oh. Oh, I'm sorry. It's because it's already in memory. Let me clear this out. I think that's the problem. No.
Well, you printed it before you redefined it.
I know, but
Yeah, you'd have to print it after your times object, wouldn't you?
oh, you're right. Yeah, sorry. Okay. Hopefully this will work. There you go. So now you just have the regular delta values from the start of the file. And then the second bracket there is showing after the conversion, passing it through this num_to_date function. So you actually, this is nice because we've had this thing in ARM called base time and time offset that a lot of people have been dealing with for years. You actually don't need to use that in Python at all. So you can just ignore those completely, use the time variable and the units, pass it to this function, and you're good to go.